about this later, and it can detect errors. TCP has checksums for header and data like UDP actually, and segments with invalid checksums are discarded. Each byte that is transmitted also has a sequence number. So, if some intermediate sequence number is missing, the receiver knows that something has been lost. So, to the lower layers, TCP handles data in blocks, the segment. So, this is where the packets actually originate, this is where the packet originate, but to the higher layer, TCP handles data as a sequence of bytes and does not identify boundaries between bytes. So, higher layers do not know about the beginning and end of segments. So, to the higher layer it is just a stream of bytes. So, let us say the application it writes 100 bytes, then it writes 20 bytes. So, all this goes into a queue. So, queues of bytes to be transmitted, and then TCP transmits them. At the other end also there is a queue, and then the above application it reads, let us say 40 bytes at each go. So, so they do not, so these 100, so to this application this is a byte stream, to this application also this is just a stream of bytes coming in such units. Now, more about the TCP segment. The unit of data transfer between devices using TCP is a segment. So, it is 20 to 60 bytes header followed by data. 20 byte header if there are no options, and up to 60 bytes if it contains some options. So, there can be up to 40 bytes of option. So, the header naturally contains some field which allows the TCP protocol to run. So, we will look into the details of this header. So, you have the header has a 16-bit port address, source port address, 16-bit destination port address, a sequence number, acknowledgement number, header length, reserved bits, some flags and then there are some options like window size, checksum is already there. So, window size is there, checksum is there, and urgent pointer. So, that is 16-bit, and then there are options and padding. So, looking at them one by one, there is a source port address. You remember from our discussion about client server that processes actually communicate through ports, and the port and the IP address together form the socket which uniquely identifies every session. Now, when a TCP session is going on, so on both sides there are two port numbers are assigned. So, to start with, you remember that for standard applications the first communication will start on well known port numbers, then they will switch to ephemeral port numbers in case of concurrent servers. So, anyway, so there is a source port address which is a 16-bit address, defines the port number of the application program on the host that is sending the segment. Similarly, of course, there is a destination port address which is again 16 bits. So, port number as you remember that is up to from 1000 to 65,000, those are the ephemeral port numbers. So, it defines the port number of the application program on the host that is receiving the segment. And then there is a sequence number. This is a 32-bit sequence number. It defines the number assigned to the first byte of data contained in the segment. During connection establishment, a random number generator is used to create an initial sequence number ISN. As you note that the sequence number, the field for the sequence number has been kept quite big, 32 actually, and that is with a reason. If the sequence number were very small, if the number of bits for the sequence number was small, then what could happen is that when a particular process session starts, so it is sending and then it would go back to the beginning. So, it would naturally for any finite length sequence number, after some point, at some point it is going to go back. Now, if it goes back and starts these numbers once again for a very small segment size, what might happen is that first of all, two packets may get the same segment number which are on the network at the same time, and similarly other kinds of confusions might arise. So, what is done is that actually a large sequence number is generated, so that even if it comes back to a low number, we know that which one came earlier and which one came later. If after receiving some very high numbers you start getting some lower numbered sequence numbers, you know that it has looped back. Actually, this is not a strict loop, this is used as some kind of what is called a lollipop. Anyway, so even without going into the details, so this is this range of sequence number. So 32 bit of course gives you about 32, 2 to the power 32 is about 4 trillion, so which is a large number, and a random number is used to generate the initial sequence number. This initial sequence number, so that it's expected that in such a large range it is not going to clash the initial sequence number. So this ISN, and this ISN is exchanged between the two nodes. So about the details of the exchange we will see later. And then there is an acknowledgement number. Just as the segments which are being sent, they have a sequence number. Similarly, these segments, as they arrive on the other side, they will get acknowledged. So one acknowledgement after another will, so a stream of acknowledgements will come. Actually, in the best of circumstances, there will be as many acknowledged numbers as there are segments which are sent. So this acknowledged number will also start somewhere, and that would be communicated by the receiver to the sender in the connection setup phase. So that is also a large number, the 32 bit number. It defines the byte number that the receiver of the segment is expecting to receive from the other party. So this is the standard norm for the sliding window protocol. We have already discussed sliding window protocol earlier. We will just have a quick look for refreshing that later in this lecture. And the next field in the header is the header length, 4 bit. It indicates the number of 4 byte words in the TCP header. This is required because the header is of variable length. The header, as we have just noted, could be anything from 20 bytes to 60 bytes depending on the options. So the header length is to be specified, and then there are some reserved bits for future use, followed by some pointers, okay, followed by some flags. So there are defined 6 control flags, ERG for urgent pointer, whether the urgent pointer, whatever is there in the urgent pointer field, whether it is valid or not. So this has to be set. If the urgent pointer is not valid, the urgent pointer field itself may contain some garbage. Acknowledgement is valid or not. PSH is request for push. RST is for resetting the connection. SYN, the synchronize the sequence number, and FIN to terminate the connections. These flags are used for setting up and termination of connections. We will come back to these later on. Then there is a window size, 16 bit. It defines the size of the window in bytes that the other party must maintain, okay, and it is sort of controlled by the receiver. So the receiver gives the window size. This window is of the sliding window protocol. And then there is a checksum which is 16 bits. It contains the checksum. The checksum is just like UDP. The urgent pointer is a 16 bits, valid only if the urgent flag is set. It defines the number to be added to the sequence number to determine the last urgent byte in the data section of the segment. And options is up to 40 bytes. Option could be single byte or multiple bytes, and it may contain maximum segment size, window scale factor, timestamp, etc. if it is multiple bytes, or it just simply shows as in a single byte the end of options and no operation for padding purpose. So end of option is used for padding at the end of the option field, and no operation used as a filler between the option. If there are options on the other hand, one option is maximum segment size, defines the size of the biggest chunk of data that can be received by the destination of the TCP segment. This is the size of the size of data, not the segment. So, which is I mean taking the header field out. Window scale factor defines the size of the sliding window and how it is to be changed. More about changing window sizes later on. And timestamp filled by source when segment leaves and destination returns it in the echo reply field. This allows the source to determine the round trip time. This round trip time, some estimation about the round trip time is very essential, because once suppose, I mean if we are just talking about the error control through acknowledgement, suppose a particular segment has been sent. Now it is now the sender is expecting an acknowledgement. So if the acknowledgement does not arrive, but the question is the acknowledgement does not arrive by what time? Okay, how long would the sender wait for the acknowledgement to come? So you have to make an estimate, and that estimate is based on the round trip delay. Okay, so maximum segment life, so twice that, so that much it has to wait, maybe some more, and only then the sender would sort of come to the conclusion that maybe that original packet is lost, or maybe even the acknowledgement is lost. But in either case, the packet or the segment that was sent, it has to be retransmitted.